All right, I'm going to get started. So I am delighted to introduce Will MacMahon for our department seminar speaker today. So Will actually started his geological career here at Imperial. So I think you were like the first cohort of students I took to Calabria years ago.
Surprised it wasn't the last cohort, but yeah.
You did a great job. So since then, Will did his PhD in the University of Cambridge, working with Neil Davies on pre-vegetation fluvial dynamics. Since then, you've done postdocs at Utrecht and also in
Hull, very
right?
briefly during the
and
pandemic.
you've been in Cambridge and then back now in Cambridge as a research fellow at Clare. So I'm really keen to hear about what you're going to talk about today.
Great, yeah. Well, thanks very much, Alex. I was saying it's a real privilege for me to come back and see how much the department has changed in the sort of 6, 7 years, or more than that, 8 years that I've been away. And yeah, hopefully I can make you at least interested or intrigued in some of the problems that I've been thinking about ever since I left in 2014. And yeah, I'm going to talk to you a little bit about how the first evolution of land plants through the Paleozoic essentially changed the game when it came to the functioning of the Earth system, and how those changes are archived in Earth's global sedimentary record. But I also want to spend a good amount of time thinking about how if we actually subtract all of that life, subtract all this greenery here in the nice Saskatchewan river crossing, which by the way makes a really great coffee spot when you're on holiday, how all this greenery actually impacts these environments. But if we just removed it, what's the sort of abiotic skeleton that kind of underpins all of these surface processes? How would things have been different throughout the sort of 85, 90% of Earth history where this sort of plant life just didn't exist? And then also, you know, we subtract all this vegetation. This is one sort of like difference than when we start to come look elsewhere. Start to look to other rocky planets where their sedimentary records are increasingly accessible due to fantastic efforts, rover missions, orbiters, the likes. How can we actually use the sort of tangible but accessible, touchable records on Earth today to start asking some sort of bigger questions about how sedimentary processes are sort of fixed on other planets? Okay. But to do this first, we need to maybe get a basic or more of a basic understanding of what the sedimentary rock record actually is. Okay, how we actually use it and how we can actually ask appropriate questions rather than sort of ignorant questions, if we like. So I'll kick off. You know, what is the sedimentary stratigraphic record? Well, you know, map of the Earth. Essentially, it's all of this. Where's my laser point? There. It's all this green stuff. This is a map of the USGS. Sedimentary rock cover, or sediment cover at least, you know, vastly outweighs, you know, metamorphic terrains or plutonic terrains. We've got a thick, accessible reservoir of information here. But more so, here we go, it spans 3.8 billion years of Earth history. You know, we go places like the Isua Greenstone Belt in Greenland, you know, Pilbara rocks in Australia. You know, the sedimentary rock record goes back 3.8 billion years, okay? This is longer than the evolutionary domains of plants, of animals. You know, only microbial life might actually be a greater expanse. So we can actually, you know, study the sedimentary record to see how, you know, things like the first evolution of land plants, the first evolution of macroscopic life, how these sort of things interacted with their environment and kind of changed the game, okay? And then when, you know, sedimentologists go off in the field, stratigraphers, the people left behind, what they think we're dealing with is, you know, beautiful rocks like this, all right? This is the Fish River Canyon, taken on my 30th birthday last year. And yeah, you know, we've got masses of rock here, you know, kilometers of strata. We can trace environments downstream. We can, you know, do all manner of correlation, 3D architectural reconstructions, 4D temporal reconstructions. It's a playground for sedimentologists. In reality, we're often dealt with this, all right? This is Bradgate Park on a rather grey day in February, a couple of weeks ago, start of February. You know, small little outcrop on the lower side of a hill fort, okay? But, you know, this is what we often got, and it's really, really important that we know how to actually work with small reservoirs like this, because it's, you know, these, you know, sedimentary terrains that span the world, often they're little discretized, scattered little outcrops like this, but it's really important to try and understand, you know, how they formed, because in the instance of Bradgate Park, we used to take undergrads to Charnwood. I'm not sure if that's still the case. They host some of Earth's earliest macroscopic life. So we want to know what sort of environments that life was evolving in. You know, we want to ask serious questions about, you know, how these tiny little rocks formed, which are orders of magnitude smaller than the original geomorphic processes that formed them. What sensible questions can we ask? Now, it's important that these sort of questions sort of bear a place in reality, because sedimentologists, increasingly, I think it's fair to say, get a little bit of a rep for being sort of living in a fairy world, sort of overly qualitative. Stuff like this doesn't help, you know. Here's a little hillside outcrop in Shropshire, crevasse splay deposits on a prograding proximal brave plain. I won't say who said that. It's not. It's a lichen-covered weathered rock on the side of a path. Okay, it's really important that, you know, we appreciate what information exists in our rocks and what information doesn't. If we have a hope to actually get to the original geomorphic processes that formed this thing 540 million years ago, we need to bear our sort of like interpretations in reality. Now, it's not just sedimentologists that sometimes have this sort of reputation for you know, coming up with rather dubious, unfaithful interpretations. Often it's very, very common to view the entire sedimentary rock record as being unfaithful, unreliable, scattered, you know, as in, can we actually trust the signals that we're actually seeing in outcrops, however large they are? This is a nice photo taken on Christmas Day last year in my neck of the woods back home. This notion that the sedimentary rock record is unreliable, it's got a lot of momentum recently, and it started with this, you know, pretty awesome paper, really, led by a guy called Derek Ager. He basically noted from the lower lias in the Vale of Glamorgan, from these outcrops, that when this sort of sandier band that we can all see that had been interpreted as just sort of like wave-forming shoals and bars in a subtidal environment, he said no. He said, let's actually think about this, and got a date for the base of the cliff and a date for the incoming of this overlying sands, and saw there was 9 million years worth of time. Okay? So when I was there on Christmas Day, the sort of thing I do, I counted the beds broadly. You know, I was, you know, Christmas Day hangover, it's fine. But I counted 35 beds, all right? So 9 million over 35, that's 257,000 years per bed, okay? And the fact that Derek Ager appreciated this, he said, actually what we're getting in the rock record, it's unreliable. Actually, what record we exists are these big sort of catastrophic processes, big mass flow deposits in this instance, but not the everyday mundane sort of situation, okay? That's the rock record we have, we can't reliably trust to look at signatures of how these processes were functioning in this instance back in the Cretaceous, Jurassic. I want to try and convince you that it's not true. He did come up with pretty much the best conclusion of all time. It all happened on one Tuesday afternoon, all right? It's an awesome conclusion, all right? But I hope for a case study, you'll appreciate I don't buy this, okay? So we're going to jump over to the Red Crag, or the Crag group. Cambridgeshire, we're not blessed with like fantastic geological exposures like the Fish River Canyon. We get little sort of, well, it's fenland. We have to go to places like Suffolk and Norfolk to even get any sort of outcrop. And the outcrops we kind of get are sort of like this, sort of disused quarries made for agricultural processes. Also, you know, nice little coastal outcrops. Amazon have just recently constructed a massive mansion to film a vampire rom-com or something on this cliff in Bordsey, and it's since retreated about 10 meters. The locals are very unhappy. But you know, these are the sort of outcrops we have to deal with. But they are very, very useful outcrops in telling us exactly what sort of processes were existing in this part of southeast England back in the Pleistocene. Okay. So what do we actually have? All right, I'm not going to dwell on this. But essentially, we're preserving subtidal or tidally influenced environments. We have nice cross beds, big slit faces, moving of former dunes. We have a lot of shallow lag. We have tidally influenced currents, things like flays across strata, even some herringbone across strata. Essentially, these processes are pretty mundane across the entire outcrop belt, all these little scattered outcrop belts across the southeast England, across that coastline. So sedimentary processes attest, you know, pretty sort of mundane, usual tidal environment. But Trace fossils add to this story. Okay, I like trace fossils. Trace fossils are cool. Whereas the sandy packages, you've got a meter package here on this top left. You can look at these bed forms and think, oh, that might have formed in an hour. Oh, that might have formed in a day. You can look at modern analogs for that. Pretty much every single one of these surfaces, all right, is burrowed. Okay. What that's telling us is there's hidden time within this outcrop. Okay. Not only is sediment, whenever we see an outcrop, we think, deposition. All right. Maybe we think, oh, that's a nice bedding plane, that's an erosional surface. Okay. The trace fossils, they're not going to build their home. It doesn't matter what they are in this instance. They're not going to build their home in an active sedimentary environment. They're not going to build their home in an eroding environment. They want sedimentary stasis. All right. Nothing going on. Okay. And this story of stasis, we'll see now, will add up exponentially the amount of time actually preserved in these outcrops. All right. So these trace fossils are scattered all over these bedding planes. Even sometimes they've been eroded a little bit, but there must have been stasis beforehand for that burrow to take hold before that erosion would happen. So when we appreciate that these sedimentary outcrops are built up of deposition, of stasis and erosion, we can start playing some fun games. All right, so this is a little sort of like thing we pulled together. All right, again, just a random disused quarry on a farmer's land. All right, and we're going to try and add up the amount of time between these blue lines. Okay, this is essentially one sort of bar package with a few reactivation surfaces within it. All right, and this little diagram at the back, our little pink lines are going to be erosion, and these sort of various colors will be different sort of amounts of stasis, different temporal durations of stasis. So let's work chronologically. All right, we have a series here of prograding bar surfaces. All right, now we can look at modern analogs and say, all right, bars in tidal environments, they could move a few meters in an hour, a few hours. All right. Each of these slip faces is unburrowed, has no trace fossils. All right. What that probably is telling us, because it's the same environment, it's the same sea, the same coastline, is that the amount of stasis was pretty short. All right. The burrows didn't have a chance to come and say, hey, it's a good place to make a home. All right. We got a little erosional slip face. That's great. But again, it's broadly concurrent with the deposits below. So we're probably not losing much time here. And we have these three blue lines. Now, these are burrowed surfaces. So again, these are bar slip faces. We're now looking into a bedding plane or into a foreset rather than adjacent. That's the slight difference in angle there. But every single one of these blue surfaces is burrowed. And again, modern analog will tell us those burrows would take between the order of sort of minutes or hours to form. Okay, so every single one of these sandy packages might have taken only, an hour to deposit, but there's hours of time separating each of these. All right. Again, black lines, foresets with no burrows, a little more erosion, foreset with a burrow, more time, lots more foresets, no burrows. You start adding all these things up, and you tend to get to about, in this instance, we calculated about 20 days. 20 days worth of time in one small outcrop in Suffolk. Okay? Now that's fine, that's all well and good, but what's that mean for how we view outcrop belts, sedimentary records in general? All right, ignore that. Okay. So let's view the red crag lithostratigraphically. All right, this is the red crag, this little block. And we have a tendency, in geology, appropriately, to view the oldest rocks at the bottom and the youngest rocks at the top. All right, 600 to 800,000 years is about the sort of time period we're talking. That separates the oldest bits of red crag, the underlying geology, from the overlying geology. All right, park that thought. This little diagram on the top, this is how we actually view outcrops. All right. The pink is essentially indicating that we've had an outcrop that's, we've had some sediment that's deposited, right? And this outcrop belt spans from the north to south. All right, this outcrop belt. But the outcrops themselves, all right, I've highlighted in yellow here. They're small little discretized windows. They're snapshots, all right, that we can actually go to and look on a coast, on a disused quarry, whatever, and actually try and interpret the sedimentary processes, okay? Now let's start thinking about erosion and stasis and bringing that into play. Instead of considering that time is oldest at the bottom and youngest at the top, in reality, across these outcrop belts, time is smeared laterally. All right, we're depositing in very, very, very small environments, small pockets at any one time. All right, so we might, the pink is deposition, just to deal with the top layer for the time being. This is the topmost strata. We might be depositing in this little spot for a while. All right, meanwhile, nothing is going on elsewhere. It's all stasis. All right, then we're going to move over here. Then we're going to move over here. Then we're going to move over here. Our system is autogenically switching all the time and changing the locus of where our time is actually being preserved. Okay, So when you start adding up all of these little sort of pockets of time, if you like, these windows of time, suddenly the days and months preserved in any different outcrop start adding up. All right, they start getting towards this greater number. And then when you take any one of these individual blocks, let's just take this pink block for a minute, as we showed with the trace fossils, it's not actually all deposition, right? These red lines are meant to be just indicating high atoll surfaces, erosional plains, bedding plains. But if we actually view those bedding plains in terms of time, all right, any individual outcrop will be made up of deposition, stasis, erosion. It's a hodgepodge, a patchwork of all these different processes that accrue, you know, weeks or months of time, which then progressively add up and add up and add up and add up, such that our outcrop belt starts to get back to the sort of like that grander period of time, in the case of the red crag, a couple of 100,000 years. Okay? It's this appreciation that the bulk of our time in any of these outcrops isn't erosion and it isn't deposition, it's stasis. Ignore things like this. Just because we're not depositing in this 2D vertical section here, we might be depositing somewhere else, probably Lyme Regis. All right? Plenty of outcrops that aren't on a coast in Wales where you can take a photo on a Boxing Day hike. All right? Subcrop. A lot of time is hidden rather than lost. Okay? But what this means is we can really trust the rocks we're seeing to preserve really high resolution pockets of time. Okay? And when we start appreciating that, we can start applying it to some rather interesting concepts. All right, so time gaps and deposition within any stratigraphic section can be contemporaneous with deposition of strata elsewhere. All right, essentially, if we're not depositing in A, we might be depositing in B. All right, park that thought for a sec. We're going to go to Mars. All right, and when we appreciate this, we can do some rather cool things. Okay, again, unvegetated environment. We'll do full circle and bring it back to vegetation shortly. All right. Yeah, during the pandemic, all the fieldwork got cancelled. We had a little play about on Mars instead. It was fun. A colleague of mine, he discovered this outcrop in the Hellas Basin, big impact structure in the southern half of the globe. And he noticed, and again, some friends at the Open University kindly made this fantastic digital elevation model. He noticed sort of concave structures, right? Little things that sort of vaguely resembled channels, all right? And came to me and said, oh, hey, you know, what do you think these might be? Could these be liquid? Could this be, you know, a sedimentary rather than geomorphic evidence of rivers on the planet? I should add that the surface, by impact cratering dating, is about 3.7 billion years old. So we're going all the way back into the Noachian, into some of the earliest evidence of liquid water on the planet. Okay, so I got involved and we flattened the image, and I essentially got my crayon out and I started like sort of annotating it. All right, seeing what I had. Again, being born in reality, plenty of this sort of outcrop is covered up in scree. But look at the scale here, like 20 meters by 200 meters. There's some exaggeration on this, but this is a large outcrop. This is a big system. All right, and I'm just going to zoom in. So I'll zoom in on figure 3A from the paper. All right, and these are the channels in question. All right, unannotated and annotated. Ignore the red lines for the moment. If we just focus on the blue, all right, we actually have evidence of not only our channels, all right, which are about 15, 20 meters deep, all right, but actually evidence of them laterally moving. This is a former channel bank, and that's moved laterally to its final position. It's degraded, it's filled with sand. There's little erosional surfaces within there too. It's a nested channel. There's periods of erosion and probably stasis even within this one channel. They're asymmetric. We've got gentle sides and steep sides. Same on the bottom. Gentle sides and steep sides, right? That might be indicating that we've got some sort of curvature. There's a lot of information that we can get from this outcrop, despite the fact that it's covered in drift, 3.7 billion years old, and on a red dot in the sky, 160 million kilometers away or something, all right? But we can take this further, all right? Gentle side, steep side, that's implying some manner of sinuosity. Well, again, appreciate the image is fuzzy, red dot in the sky, 160 million kilometers away. It's pretty good. But we have inclined surfaces, all right, that run adjacent or run parallel to these channelized structures, all right? And we interpret these as form of bars, all right? They have distinct, right, here at the bottom, top set, foreset, and bottom set elements, all right? They prograde laterally and actually have internal truncation surfaces within them to suggest that we have a period of migration. It stops, a period of migration, it stops, and so on and so forth, all right? We have stasis locked up in this environment. So yeah, we interpret these as essentially lateral accretion surfaces. All right, these are a signature of sinuous channels, of meandering channels on Earth. This is just a nice example from Siberia. But essentially, as flow is centrifugal, flowing water is centrifugally deflected around a river bend, we cause basically helicoidal circulation patterns which erode the outer bank, and a secondary current comes into play and causes inner bend accretion. We deposit on the inside bends. And they make really, really nice sigmoidal patterns. Okay, here's just a nice example from the Carboniferous. And this tells us, great, right, we've got water on Mars. Cool, we already knew that. But we can go a step further, all right? These sort of like inclined surfaces, this sort of architectural detail on Earth, we associate more with river discharges that are sort of perennial, all right? They're long lasting. We don't have a massive flood on our hydrograph followed by a quick wane, all right? We just had episodic ephemeral outburst floods, i.e. we deposited for a day every 100 years. These sort of surfaces, they would all get muted, they'd get erased, they'd get removed. The fact that we're preserving this architectural detail, just like we would on a geomorphic surface on Earth, is implying that what we actually have is perennial rivers, right? Long-lasting, sustained fluvial flows, okay? So big rivers lasting for a long time. Let's bring stasis back into play, okay? Time gaps in deposition within a stratigraphic section, contemporaneous with deposition elsewhere, okay? Now we're just playing about with it on Mars. Same image, all right? This time I want you to focus on where these channels are actually sort of distributed through the outcrop. We have a series of channels here, all right? Probably a series of channels here. They're separated by much larger, this dotted black line, much larger surfaces that essentially expand much further along the outcrop. Again, they probably correlate here. There's lots of drift sort of getting in the way. Lots of drift down here, but there's probably similar clusters of channels down here, okay? These essentially define channel belts, all right? And a channel belt is essentially the area in which a river will do work in between avulsion events. You know, we're doing work in one spot or a few spots, and then something happens upstream and the river says, hey, I'm done with being here. I'm going to go over here instead, all right? Then we lose that deposition here. But it's not like the river doesn't exist anymore. It does. It's just depositing elsewhere in an outcrop that's either not, you know, exposed at the present day, or it wasn't spotted by bored geologists during a pandemic. This time is not lost, it's hidden, it's elsewhere. So whilst an individual channel belt might take of the order of 10,000 years to form, so perennial systems working for 10,000 years, multiple channel belts, all separated by this stasis surface where this system is working elsewhere, suddenly the amount of time where water is active in, you know, there's evidence of water in stratigraphy increases exponentially, which is really, really interesting in terms of, you know, looking for life elsewhere, et cetera, et cetera. Yeah, there we are. I've jumped the gun. Each of these surfaces indicates stasis. So remember that time is smeared laterally across the outcrop belt. We're essentially looking at one outcrop, that's here, but all these other locations are undergoing stasis, and occasionally we're done being over here and we go and deposit over here instead. It's going to link back to vegetation shortly, I promise. I tried to pitch this on Fox News. I pitched it totally wrong. If you want, it was lost on them. If you want a funny giggle, it's a very easy YouTube video. Stasis gives us one more thing, all right? And that's beautiful bedding planes, all right? Really, really, really high resolution snapshots of surface processes, okay? These are all from Raundsey Quartzite, Flinders Ranges, location where you can go and study some of the earliest animal fossils. That's two species of Dickinsonia. These are pteridinian fossils. There's some of the earliest macroscopic life. We don't have time to talk about them today. But you know, we preserve these when we have intervals of stasis, when the next bed hasn't come along and completely eroded that sort of preceding stuff, all right? But we get these really, really beautiful snapshots, all right? Here's a drainage pool. So we've got large ripples flanking some smaller ripples up here. So that's where water's just pooled. Linguoid ripples. Here you might see there's some little drainage lines etched into the flanks of these ripples. They show sort of fluctuating water depths. There's a whole diversity of these really, really, really subtle sedimentary features that are really easy to get in the record. Well, they're really hard to get in the record, but there's enough time, enough space. It happens all the time. It's not unusual, okay? Now, consider scale again, because this is really important going forward, all right? Yeah, Tumbleweed Sandstone in Australia, Bude Formation in Cornwall, you might have seen them. These are both just rippled bedding surfaces. And if you saw them, you might think, hey, great, that's a really, really good surface. I can do some good work of this. all right? I can interpret many, many things about the original environment in this one spot, okay? Had the privilege to go to the Bay of Fundy last year. If you ever get a chance to go walk out at low tide, keeping an eye on the tide, it's fantastic, all right? But here's just one bar with some climbing ripples on top, all right, or some ripples piggybacking on top. And this is the sort of scale we're talking, all right? X to X dash, that's that scale. Y, that's that scale, okay? Suddenly, these beautiful bedding planes aren't looking that like fantastic in terms of like interpreting the grander scale processes going on, all right? Consider that that is the scale of C within all of the bars in the Bay of Fundy. Not all the bars, sorry, D is there, all right? So if we were to take a ripple bedding surface like this and start thinking, hey, we can interpret like macrotidal processes and, you know, all manner of things to do with the behavior of the entire Bay of Fundy, that's the sort of thing that might get flagged in review, okay? Hasn't stopped us, all right? Flashback to here, crevasse-blaze deposits, prograding proximal braid plane. These are geomorphic phenomena, orders of magnitudes larger than many of these bed surfaces, okay? And this is just Earth. This is one of the latest images from Curiosity, all right? Absolutely fantastic, you know, wave-forming processes on another planet, definitively. You know, these are rippled surfaces in a 3-point-something billion-year-old rock, you know, proper evidence of wave processes. It's fantastic. But if we start reconstructing lake processes, you know, on a wider scale, you know, from these outcrops that are only a few weeks old, these images, so nothing's been done on this yet, that's the sort of thing that gets a little bit dubious, okay? Unfortunately, we've got a good track record on Mars. This is something from the Curiosity team as well, all right? It's an outcrop known as the Shaler outcrop. You might have seen it before, talking with Sanjeev and the likes. You know, it's essentially, it's a fluvial bar form interpreted. It's about 70 centimeters thick and 20 meters wide, okay? And the work is on it's incredible. But in the abstract, they rather ambitiously say, this is the opportunity to reconstruct the paleomorphology of a fluvial environment on Mars. Okay, maybe, but you know, this is a much larger scale process than just one individual bar, you know. And they go on and talk about how stacked cosets of cross beds suggest multiple bed forms, provide clear evidence of short periods of flow. Again, tick, it's true, all right? But then they go on to say the lack of exposure prevents distinction between whether these are bank-attached bars or mid-channel bars, i.e., is this a braided low sinuosity river or a meandering river? Again, tick, that's true. Those bar-forming processes are orders of magnitude greater, all right? It would be foolish to try and go back to the original geomorphology from an outcrop like this. Let's see if Perseverance are behaving in a similar way. All right, again, this is a paper that's out in Science. The imagery alone deserves being in Science. It's fantastic. But this is a Perseverance image as we've reached the toe of the delta, the foot of the delta. And it's amazing, all right? It really, really is beautiful. It's not a critique. But these inclined surfaces, we interpret the presence of inclined strata as evidence of deltas that advanced into a lake. They could be. I'm not saying they're not, okay? But these inclined surfaces with discrete sort of top set, foreset, and bottom set elements, it's a process of equifinality. Multiple different processes can make similar looking products, all right? They look a lot like our lateral accretion surfaces from earlier, okay? The Perseverance team are on it. The thickness and lateral extents of the foreset units are too great to be explained by formation as lateral accretion deposits of fluvial bars. Well, those yellow bars indicate the scale of the outcrop against some laterally accreting fluvial deposits also on Mars, all right? This concept of scale is so important, all right? It's totally fine for these to be lateral accretion deposits. It's only 10 meters thick. They scale to the size of the original channel. 10 meters is all right. It's actually top truncated, so it would be a little bit deeper than that. But these are, you know, it's okay. It's okay for these to be lateral accretion deposits. Now, they then go on and say, and this is not a critique, that the overlying deposits in this outcrop are boulders, all right? So we have deltas prograding into a lake. These are rather sustained flows, but the boulders indicate episodic flows, all right? This is a change in the discharge regime indicated by this one outcrop. Again, it might be true. But if these are lateral accretion deposits, these could just be the sort of channel Thalweg or the basalmose you know, traction deposits in an overlying channel that's coming into this area, again, orders of magnitude larger than this initial outcrop. All right, it changes the interpretation a little bit. We just need to be really wary. And we certainly need to be wary of statements like this. Rover images constrain the hydrological evolution of Jertsura crater, potentially also the broader climate and habitability of early Mars. Well, can you see the outcrop here? It's there. I'll help you out. All right. It's a small scale process within a much larger system. If we're trying to constrain the whole of the sort of early climate and its change on another planet, that's a bit like me saying, sorry to compare a flagship outcrop on Mars to a disused quarry on a pig farm in Suffolk, but that's about the same dimension. And if I went there and looked at the change in the cross beds and the style in there and said, oh, this will help me reconstruct the whole of the Pleistocene history of the southeast of England, that probably wouldn't make it through. Right? These rules don't change depending on what planet we're playing on. I'm finally going to get on to plants. All right? The fact that the rock record grants us these really, really high resolution snapshots. It doesn't matter if these are, we've discussed later probably with some people here, anti-dunes or ripples. These are ridge and swell topographies formed by, again, inside of meander bands, helicoidal processes. The rock record grants us these small scale but reliable snapshots. But we have to be really, really careful when interpreting these back to larger scale processes. But the good thing for us, people interested in life, and I'm finally going to get onto it, is these small scale processes accrue, all right? As we look at sedimentary basins or the entire geological record, where's my laser pen? There we go, all right? These large scale processes, these big things where we think, okay, what influence basin fills? Well, tectonics, sea level, climate. Well, in actual fact, when we get down to the bedform layers, this is what we're preserving. We preserve these pretty well, all right? High resolution snapshots that, beds propagate up and form bars. So we get snapshots of bars, they propagate up again and get belts propagate up and make basins, all right? But this lower order stuff, or this small scale stuff that essentially makes up a patchwork quilt this large, this lower order stuff is influenced by life, all right? So the fact that we're influenced by the local scale and that propagates up the hierarchies, that means that when we're dealing with sedimentary products on a big scale, life is a very, very important player that we can't ignore, all right? I'm going to show you an example, all right? So this is the Platte River of Facey's model fame. I just found these a few days ago, 17 years of, history of the Platte River. Notice we've got nice sort of vegetated islands up here, okay, vegetated islands, nice big riparian forest, okay? And these riparian forests essentially is having an influence on how these channels are behaving, all right? If we have a look in 2011, all right, we've got this nice little anabranch here, this nice little vegetated island, and despite all the floods, it's there as well. Everything that's come in the subsequent 2 years, 4 years down here in 2015, it's covered up by my slide, that island is persisting, okay? It's not moving, okay? And then in 2016, someone decides, oh, I'm going to have a way of that forest. I'm going to cut it all down and I'm going to turn it into a farmland, all right? We've removed that vegetation, and as a result, we widen the river course, all right? Vegetation essentially sits, the river suits the new equilibrium. We've widened all these channels such that once we've undergone a little flood, all of these islands suddenly can't resist the erosional forces of the new river, the new discharge. The river has widened, and all of these nice vegetated anabranches are now actively moving braided streams. Just that one little tweak of vegetation, and we've changed the influence of the system. But it's not just because of the system. I'm going to mull over this. It's because of all of the small scale processes that are going on and accruing up the orders of magnitude, okay? It's this effect of plants. So these are really, really fun images, all right? This is a moss taken under the scanning electron microscope, okay? And all of these little particles here, you see a particle, 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 particle. These are clays, all right? And the vegetation has acted as a trap. It's what we call baffled the clays that are in flow, caught them and forced their deposition, okay? We can see the same thing going on here. This is a flume experiment back from my time at Utrecht. These are alfalfa seeds, all right? And in these flumes, we chuck these little bits of plastic. It's only a flume, just to trace where sediment's moving. It's hard to trace an individual grain of sand. We use this. And once the experiment's over, you can see that a lot of these little bits of plastic have been caught in our alfalfa seeds. Certainly a lot's been caught behind it. Vegetation is eco-engineering the environment, all right? And it's not just what's going on above ground, it's what's going on below ground. This is mechanical, the roots are actually adding to our mechanical stability. And actually, again, these are clay material adhering to rhizoids or root hairs, all right? And once you adhere a little bit of clay, it's really cohesive, it's sticky, so more clay will stick to that, and then you essentially start a positive feedback loop that goes on and on and on and on and on, all right? And lo and behold, these processes add up. all right? You add vegetation to a continent, suddenly you add essentially the flow resistance to your landscape, you build up topographies, and you essentially cause a funneling effect. You make it harder to maintain multiple threaded channels and easier to make nice meandering channels like this. And that shows in the rock record, all right? So VS, don't worry about it, it's just essentially a vegetation stage, a stage of which plants are coming onto the continents back in the Paleozoic. And in the earlier times, in the Precambrian and the Cambrian, we have very little of these deposits, all right? And as a result of that, a lot of the interpretations of old suggest these are sort of lower sinuosity multi-thread systems, all right? Vegetation progressively comes on the scene through the Ordovician, Silurian, Devonian, and suddenly the amount of interpretations of meandering rivers is on the up, okay? We see a sort of state change in the rock record's behavior, and the reason we see it is because the rock record is providing a very high resolution snapshot of a small scale process. So you can go and look at all these small scale processes in all these different places around the world, and they accrue up and up and up and up and up the orders of magnitude to make the global rock record. Vigilant of time. Someone in the audience is thinking, but hang on, there are meanders on Mars. Okay, presumably there's no vegetation on Mars. Someone's definitely thinking it. Fine, let's deal with that elephant in the room early. I'm amazed I made it 50 minutes in, or however many minutes in, without mentioning the Torridon. It's my PhD area, absolutely love it up here. Usually I'm focused up on this Applecross formation, but of late I've been pushing down in stratigraphy into the diabac. Some of you might have seen this. It's a leucostraton unit with a lot of fluvial channels essentially feeding this system. But the behavior of the diabac is pretty cool. If you look at the Lewisian gneiss, this is the oldest rock in the UK. It forms a really cool paleotopography, a rugged paleotopography that you can actually map out its topographic highs, its topographic lows. And the diabac, or this brown and gray, it's essentially filling in all of these paleotopographic lows. All right? But the topographic lows do something cooler. They make the basin somewhat hydrologically closed. Whereas in the Applecross, where everything's open, essentially we've got connectivity to the oceans. These paleotopographic highs make it very hard to get sediment in and out of the system. We're depositing into our lake environments. Okay? But it means that the muds that would maybe be bypassed off into the marine realm, here they're getting trapped. They've got nowhere to go, all right? So they start building up floodplain topographies, all right? They start sticking to each other, building up the landforms, and suddenly we're changing the behavior of the rivers that are going on. Suddenly we have landscape stabilizing muds in the absence of plants, okay? So what do the architectures look like? Well, this, okay? This is a channel fill, all right? Essentially, this is the basalmost portion of the channel. Is this stuff. This is the classic facies finding upward diagram of John Allen of old. But essentially, this is the tractional bottommost deposit made up of cross beds and the like. We go up, and then we start actually preserving these nice lateral accretion surfaces. Here they are down here. These are inclined surfaces that are perpendicular to the regional paleoflow, i.e. they're forming on sinuous bends. And we even have this beautiful ridge and swale topography. This is a geomorphic signature of inner bend accretion. This is due to those helicoidal flow processes that happen as a result of meandering. And these geomorphic signatures are all over the diabac. You know, here's a beautiful little ridge and swale topography preserved in sort of top down. Again, here, if you follow my pen, up, down, up, down. I don't think I've got another little thing. These are meandering systems, right? And the reason they're afforded the ability to meander is because there's a lot of mud trapped in that system that's providing the flow resistance, you know, which on other pre-vegetation landscapes just doesn't exist, all right? Let's skip that. But they're very, very transitory, all right? Essentially, they'll last as long as this endorheic basin, this closed basin, has space, all right? This is essentially a little schematic. This is the paleotopographic low. That's filling with some coarser stuff. All this gray and the blue, this is the meandering signatures. As soon as we fill up this basin and fill up this basin, diabac source from the Lewisian topographic highs, all right, it shuts down. Then we get the Applecross. The Applecross has a more distal source. It comes from the Grenvedian mountain belt, all right? Here, all of our fine material is being bypassed off to the marine realm. It's not knocking around long enough to provide stability to the landscape. So instead of like being confined into one single thread meandering channel that can sort of comb its sort of environment very, very slowly, geologically speaking, suddenly we have low sinuosity braided channels that are capable of this. So the architectures of the sand bodies just look way different. We don't have muds, or very few muds. What we have are laterally extensive sands as these channels are moving back and forth, biasing the record to the channel bottommost position. And occasionally we get an avulsion event. And at that moment, we preserve beautiful bar form topographies like this. This is about 50 meters wide, and it's interpreted as braid bar, where we're getting lateral flanking, big accretionary surfaces on each side, lower topographies in the middle. So this would be one channel belt. All right. The sort of reason we had meandering lower down was due to this heightened flow resistance provided by mud, flow resistance that vegetation at later geological stages provides. But once we get into Applecross deposition, this flow resistance, we lose it. Cool. So what's this got to do with Mars? Well, on Earth, we have a range of exhalaic, hydrologically open basin types that form due to subsidence and the likes. And essentially, these sort of open basins facilitate the bypass of mud downstream. It doesn't hang about long enough necessarily to influence river systems. I'm talking Precambrian here. On Mars, a lot of our sediment fills are confined to impact craters. So a bit like our Lewisian topographic lows, these impact craters, like the Dirtshire Delta, they're prohibiting the sort of bypass of all this fine material. It's more likely to stick around and actually confine our channels to individual spots. It's more likely that we're going to provide the flow resistance necessary to actually allow these self-sustaining meandering channels. And again, not all the geomorphic signatures for rivers on planets are confined to impact craters. This is Aeolis planum, I believe. It's an open plain. But again, these meandering channels, they owe their origin not to progressive weathering of some hinterland, but due to something like a crater lake breach. Their source is entirely different. The muds in the surrounding area that we can identify, they've been knocking around for tens, hundreds of thousand years, I'm not sure. All right. Suddenly we have a crater lake breach or something more catastrophic, and we are depositing for however long we're depositing. These clays are brought into play. All right. Just because we don't have vegetation on Mars and we don't have vegetation in the Precambrian doesn't mean they're directly equatable. All right, which is a common theme in Precambrian research at the moment. It's a buzzword that we like throwing out in abstracts and conclusions, but not actually thinking about. I've got 5 minutes. Do I have 5 minutes? Am I right? Yeah? Yeah. Cool. All this comes back to mud, all right? Whether it's through baffling, binding, essentially this is all about mud. And this is quite an old paper now, but essentially each of these little dots on the screen represents some continental deposit somewhere on the planet. All right, spanning about 3 billion years of Earth history, Archean through to the Carboniferous. And in the Precambrian, we just don't have very much. This is volume of mud rock on the y-axis. All right, then plants come into play, Silurian, Devonian, Carboniferous. We still have sandy stuff, but we have a lot of muddy stuff as well. All right, there's a step change. And the reason we can see that step change, we can see a change from sandy stuff to petrolithic stuff, is because this rock record is a quilted patchwork of all of these little small-scale processes. And these small-scale processes are impacted at a local scale by things like plants. Adding them onto the scene has a profound effect into how the global sedimentary stratigraphic record is put together. And what I'm working on at the moment is, whilst a lot of people buy that this is due to retaining more plant rocks, mud rocks by processes like baffling, stabilizing, I want to work out, could this step change actually be due to heightened chemical weathering as plants are coming onto the continents? All right. We know that at the present day, plants facilitate chemical weathering. It's a process that happens, it exists. So they now make up 87% of Earth's biomass or something. Bringing them onto the scene must have had an impact. All right. To do this, I'm trying to get into the petrological records. These are new images. Essentially, again, this is the Applecross and Diabetic formation. We're selecting samples, and we're using a sort of new era, new generation of scanning electron microscope, energy dispersion, spectroscopy, whatever, to actually look at the type of clays that are making up our rocks. Certain clay types can only be formed physically, it's breaking down bigger particles into smaller ones, and others form through neoform to orthogenic processes, replacement processes facilitated by biotic soils. I'm aware I'm out of time. But essentially, the signatures that we're seeing in the Precambrian rocks align with our view of detrital minerals, all right? These are all illites, all right? They're essentially these lighter greens, sorry. They're aligned with flow. They've been put into place. Whereas all these sort of darker, sort of turquoise-looking colors, these are clay-sized feldspars. Now, at the present day, feldspars are the first things to be chemically altered. They're the first things to change into kaolinites and other clay mineral types. The fact that they're here in such abundance in the Precambrian might be a signature that the physical makeup of these mud rocks is different in the Precambrian to the Phanerozoic. All right. So what we want to do, or what we're trying to do, is build up a data set of mud rock petrology across this critical point in Earth history to see if there's a step change in the sort of basic constitution, the basic fabric of Earth's mud rocks that suggests that there's a little sort of transition in, how plants are producing soils. I'm out of time. Bars also get muddier. We can link this to heightened sediment supply, and I've run out of time to do a video, I think. Do I? Everyone need to run off? This is my final slide. Let's do it. Oh, no. How do I show a video? There we go. Good. All right. So again, this is simulating tidal processes. This flume is rocking back and forth and back and forth. And what we can see in the sandier example is that these channels are very, very, very active. All right. They're laterally migrating back and forth, back and forth, back and forth. In the muddier example, where we have a larger mud supply coming in, all right, we're causing this funnelly process, all right? We're deepening our estuary, and we're essentially shortening it, all right? We have less active channels by which tidal processes can navigate. They can come in and out. Whereas here, essentially, we've reduced the tidal prism. We've only got 1 or 2 active channels. That's because this floodplain topography made up of mud now has built up, all right, and has actually changed the geomorphic planform. All right. So by increasing or heightening mud supply, all right, we've essentially changed the sort of geomorphic signature of the landforms at the present day. Okay. So in time, through time, we might be seeing similar signatures. I got into point bars, but essentially point bar deposits themselves get muddier after plants evolve. We can link this to the fact that we've actually got more fine sediment knocking about in our river channels to actually influence this environment, this environmental signatures. It's 1 o'clock. I'll stop. Thanks very much. There's more stuff. Do we have time for questions? Oh, wonderful. I'm going to grab some water whilst I answer.
I just step back through time, and you know that big evolution of Canada is just because the records better. It's like a biological problem.
What you have to remember is that's not a signature of how much rock exists, but how much mud rock exists within the rock that exists. So it's not like we have a huge amount of sand and then a huge amount of mud and then a huge amount of sand and then a huge amount of mud. It's like they're interwoven signatures. You get mud. Okay, yeah, fair enough. But if it's very, very unlikely that we've decided, as a, culture, as humans, just to build on Phanerozoic or like Precambrian muddy deposits. But we're talking about continental deposits. The rock record that exists still exists. It's why would an Archean sedimentary rock full of cross beds be any different to an early Paleozoic rock full of cross beds, be any different from a Carboniferous? They're all preserving mundane processes. Just because we have less of the one than the other. We have estuarine, incised valleys full of transgressive deposits in the Paleoproterozoic that look every bit like the same that are happening in the Paleozoic, albeit with slightly different amounts of mud. It's, the snapshots that you get decrease in abundance as time goes by, but it doesn't mean that older ones any more unreliable than, otherwise what's the point? What's the point of, go on. What?
I was going to ask another thing to do with scale. So I think essentially what we've got before is there's a kind of scale independence. If you look at small scale stuff and say we look, it's clear from the south of the vegetation stabilizing stuff. So
yeah.
Move up a little scale and change the shape of whatever bars and change the shape of the amount of material in sedimentary basin. How do you know that really holds? How do you really know that it's a scale of dependence across all these scales of vegetation matters?
Well, it's like if you look at, pick an example, but if you look at, we looked at subtidal deposits in the Pleistocene, fine, it's basically gardening, it's very, very recent stuff. If I had shown subtidal deposits from the Baraboo quartzite, which is about 1.2 billion years old or something. They're both made up of cross beds. They're both made up of, they have herringbone, they have the same true substrates, they have the same, signatures. But there are differences, such as, the younger examples have a lot more mud in them than the older. I'm going to mud, it's fine, it's my bread and butter. Now, you can look at the present day and say, all right, what do plants do to mud? Well, they trap it, all right? Maybe they help produce it, they bind it, all right? So we can actually see these processes happening. Yeah, but the rock record is essentially a patchwork of all these small scale processes. So if we look at a basin, we're not just looking at, you don't like this? But that's exactly how the sedimentary record works. I do, because it's made up of lots and lots of point bars.
Take a sedimentary basin,
Yeah.
example.
Yeah.
You can sweep a whole pile of different sedimentary basins, extensional, Poland, whatever.
Mm-hmm.
They've got dramatically different stuff.
So how would you go about explaining something like the mud rock spike after plants, which covers a range of tectonic terrains, a range of basins, forelands, intracrotonics, intramontane, it doesn't matter, range of climates, close to orogenic belts, far away from them. How would you explain that step change, personally?
I think that you two should discuss this more, and I want to make sure that other people don't want to ask questions. Emily.
There's evidence of fixed on space basins on Mars, what would you suggest channels associated with those?
Well, saying you're absolutely spot on. So things like Aeolus planum that we're looking at, Aeolus dorsa, the same. These aren't crater-confined basins, right? But the source of these channels are due to things like crater lakes breaching and actually allowing us our discharge to have a fluvial record, a geomorphic record in the first place. So it's slightly different from, go for it. No, that's fine. Okay, yeah. Great, sure, that may well be true, I don't know. Again, the geomorphic signatures, I'm not saying this is a one-step fix-all problem, that solves everything. All we're saying is essentially, it's a very, very common argument to use that because we have meanders on Mars, we must have had abundant meanders in the Precambrian. We probably did. They were leaving a very different signature to that we identify meanders in earlier records. And part of the reason that might be due to is, we found a meandering example in the Precambrian. It was in a hydrologically closed basin. A lot of the meanders on Mars are in hydrologically closed basins. Cheers.
So I was wondering about this sort of endorheic interpretation for diabag.
Yeah.
So how do you know it's endorheic? Obviously, knowing what the Lewisian paleotropic was a bit of a non-starter, we can't really tell necessarily.
Yeah.
Is it based on like flow directions, or have you got a range of azimuths that look like it's all going in the same direction?
You can map out the Lewisian topography. You can see where it's high, you can see where it's low. That topography still exists, so you can literally go along and map elevations. Whether you trust those elevations, it's fine. But the distribution of sediment fills, again, the diagrams, that's a 2D slice on a 3D thing, so it's way more complicated. But you can actually stand on a hill slope somewhere in Scotland and actually be on Lewisian gneiss and look at Lewisian gneiss across the way and look at the diabeg in the middle. And then you can say, oh, when I'm near the flanks, I've got really coarse alluvium, which passes laterally into these sort of like finer grain stuff with meanders, and then lakes in the bowl in the middle. You can see those lateral facies changes, and you can see as it fills up, then essentially you've got the Applecross coming up over above that, isn't confined by that Lewisian topography. So it's a certain amount of geomorphic. Yeah, absolutely. Yeah. I mean, one thing that does really bug me is, that the diabeg owes its origin to the origin of those paleo valleys, whereas the Applecross, which is about the same age, really, again, it's smearing time laterally across the outcrop belt. Just because the Applecross overlies the diabeg, we'll get into this later, doesn't mean, they will probably occurring coevally, the deposition. So the fact that you've got one that's related to the Lewisian and one that's not occurring at the same time with different sources, that bothers me. But in terms of, is the Lewisian hydrologically closed, the diabeg hydrologically closed? It might be partially hydrologically closed. I'm sure there was outlets and things. There's no evaporites. But you can be pretty convinced it doesn't have just a nice connectivity to the ocean.
We'll take one more question. Mike, you've got comment on the version question.
No, I just wonder if you looked at even modern river systems by provenance, because clearly some will be less clay rich than others, and that would be testing your idea.
Yeah, absolutely. I haven't done any provenance work on modern rivers, but yeah, I think increasingly it seems at the moment.
You know, there's some rivers that are coming from British type
Absolutely. So like fine sediment supplies is increasingly being shown to have an impact on what plant form we're seeing at the modern day, but also what we're seeing in the rock record. There's lots of good stuff coming out of groups working in Utah and Wyoming that are suggesting muddier parts of really well-studied formations are due to changes in source and the likes. Even things like flays across bedding, which had always been a sort of nice tidal signature. People are increasingly now saying, oh, this could just be because we're choking our system with fine material. You've got a dune that essentially is a bit of topography. It separates flows, causes vortexes, and the mud settles out in a unidirectional current. I didn't get onto it, but it was the same with my laterally accreting bars. You know, again, when we do get bars in the Precambrian, they tend to be sandy, whereas in the Paleozoic, we get a lot more sort of mud content of our bars. That can't just be linked to like some tidal ebb or something. You know, this could be a signature of actually having more mud in your system to begin with, because these are submerged alluvial environments. They're inimical to colonization by land plants. Plants won't be acting to stabilize these environments. They're essentially like-for-like geomorphic phenomena, but ones have a lot of mud and ones don't. But again, that's big picture stuff based on very small scale pockets of information, which I appreciate, Gareth. Cool.
All right, it's coming up for the last, so I think we should stop. Thank you very much, Will.